Hi everyone and welcome. I'm Martin Wennerblom, Product and Marketing Director at Inmotion Technologies, part of Sappi Group. I'm very pleased to welcome you to this session here at the FOE conference in 2026. Please note that this session is being recorded and will be available to watch on demand after the event. If you have any questions during the presentation, please use the Q&A tab. You'll find it on the right side of your screen. All questions will be sent privately and addressed at the end of the session if time allows. Now, let's move on to our next session, titled Unlocking Performance Through Advanced Thermal Engineering. This session will explore how thermal design has become a true strategic enabler in the modern power electronics, allowing for higher power density, improved reliability, and more efficient electrification. The presentation will highlight how smart cooling strategies are shaping the next generation of compact, high-performance systems at Inmotion Technologies. I'm pleased to welcome today's speakers, Staffan Holm, Manager of Mechanical Development at Inmotion Technologies, and Mattias Magnusson, Chief Engineer at Inmotion Technologies. Staffan and Mattias, welcome. The floor is yours.
Thanks a lot. Thank you. So let's start with introducing ourselves. My name is Mattias Magnusson. I work as a chief engineer, and I've been here at Inmotion now for 8 years, and I have more than 20 years of experience within electronics. And with me, I have Staffan.
Yeah, I'm the manager for mechanical design. And also I have worked here for quite many years, so 20 years plus. I'm responsible for mechanical design, and that includes also simulations with strengths and thermal simulations and so on.
Great. So we will start with why thermal management matters. It is 3 main areas. First thing is that we need to enable the full utilization of modern power semiconductors like silicon carbide and GaN. Second point is the demand of higher power density, meaning more compact designs. And last but not least, it's extremely important with thermal management for reliability and lifetime. Here at Inmotion, we have a 4-step approach where we start with what we call experience and judgments. We have handbook calculations, and then the topic for today, simulations, and the last, of course, always prototype testing. So if we start with the first topic, then experience and judgments. Inmotion has more than 60 years of experience in power electronics. We have been working with power electronics within different areas, but the last 20-25 years, the focus has been on vehicles, heavy vehicles and trucks. The first thing we do with our experience is to do a judgment of the strategy, how to cool our power devices. It could be, should we go for liquid cooling, air cooling? What type of material should we have in our heat sinks and so on? And why we do this is to prevent over designing and late changes. If we do this first step, if we don't put too much effort into this first step, it will be costly in late changes. So, second step.
Second step in this, as we call it, as a 4-step process with handbook calculations. First step, as Matthias said, I mean, we start with really looking into the history, what has worked before, and then you have to, by handbook, see, does this design work or not? And on the screen, you see it's an example. With thermal design, there are 3 different ways of transforming heat. One is radiation, the other one is by conduction, and also by convection. Radiation is the rays from the sun. Conduction is how the heat transfers through metal, and convection is how the heat goes from, for instance, a metal to air, or from an heat sink to liquid. So handbook calculations, if you look on the, let's see, on this, we will not go through the math, but anyway, to calculate the heat transferred per unit time, you have an area, and you have a temperature difference, delta T, and both these variables, they are so quite easy to get the hand on. But also you need this coefficient for convection. And this one, I mean, this is a big source for error, actually, because you get this from tables. They can differ from, for instance, for air, it can differ from 5 watts per meter Kelvin to 25. So there you have a quite large source of error, actually, doing this by calculations. But still, handbook calculations is very valuable. So what you do, and also it's quite, if you want, okay, we want to have a bit more accurate figure for this heat transfer coefficient, then you can calculate it, but it's really time consuming, because this coefficient, it depends on the surface roughness, it depends on what kind of medium you have, if you have air, or if you have a glycol water mix. It depends on the speed, highly. It depends on the speed. High speeds, you have more heat transfer. Lower speeds, you have less transfer. And it's very, very unlinear. So even though you can calculate it, but it's time consuming, and what you get is not, I mean, it's good for a rough estimation in your calculation work. Let's see. So it's quite possible. And then when you get your figure, then you can put it in. This is just a cut from an online calculator. And then you can see you have all the easy to find variables. But the hard one, I mean, it's just a box. So perhaps you can cheat yourself to think that this is as easy as finding the dimensions or the temperature, but it's really not. So, but you can get somewhere. So that's regarding handbook calculations. It's helpful, but I mean, it's a big source of lot of errors, actually, for heat transfer. So next one, if we talk a little bit about simulations. We'll not get into the math also here, but the overall general method for making simulations is FEM, is finite element method. It's a method where it's like, you have probably heard this, it's only one way to eat a big elephant. You chop it up in small pieces, and this is exactly the same. So what you do, you chop up you have a geometry. In this example, in this picture, is an F1 car. And if you want to calculate the drag, for instance, so what you do is you chop up the surrounding air, in small pieces. And the closer you get to the surface of interest, you see it's a black stripe close to the body. And that's because these elements are getting very, very small, further away from the surface of interest. They're not so small. But that's the principle how you do this with the numerical calculations, with simulations. You chop it up in small pieces, and then in each one of these blocks or elements, there are a lot of calculations ongoing, actually, and then you connect these elements to one another. It's perfect for computers. I have done it by hand. but I mean, there were very, very few elements. So, yeah. Let's see. Then come question when to use simulations, some very, very simple guidelines. I mean, you do not dig into simulations the first thing you do. Absolutely not. It's this with, make an estimation, base it on experience, use handbook. And if you want to more have accurate, then you do simulations. And what kind of, when? Complex geometries, that's a perfect example of when it's very, you have to make simulations. For instance, a finned heat sink as we have in our products, or when you transfer heat to air, or when you have a liquid heat sink. It's a complex geometry. The heat transfer coefficient, this figure, the h, the small h, it varies very much. Then it's a perfect example when to use simulations. And also point number 2, handbook calculations, they're not good enough, really. I mean, usually it is a good start to calculate by handbook, because you can see that you're in the right ballpark, so to say. But then it's not good enough, really. I mean, to choose a design. So then you have to go by simulations also to get some more precision and more. You evaluate your results. You can rely on them. And the third thing is when you have a lot of different design choices. Really, you don't really know. You have to choose design, and then you also have to optimize your design. It's really perfect to use simulations instead of making physical prototypes, because you can make, I mean, a number of simulation runs in a week or in a month, and you will not afford it, you will not have the time to make prototypes. So that's a really good thing when you have to make this kind of work, digital prototyping. So some questions that you can answer with the help of simulations is product cost to optimize. Can you use a smaller fan, for instance? Performance and product limitations. If you want to choose, perhaps it happens that someone comes and say, we need more power. Is it possible? And then instead of building a prototype, then you can get answers within a rather short time and using so limited resources. It takes time, absolutely. But comparing to build physical prototypes, it's so much easier. To optimize size, also typical question, you can say, is if it's an application, we want to make it, can we make it smaller? How much smaller? Can we change the geometry? Then also, I mean, instead of making prototypes, you make a new model and you make a new simulation and you get very accurate answers. So it's really, really good. Product performance also, I mean, as I mentioned, if we had all the components, the whole design, really, I mean, filter components, power components, and all the components that in some way, bus bars that you get, so power losses. You can simulate individual components, and you can simulate the whole assembly. So one more time, is what if analysis. It's really good. Touristic ventilation. If you have an installation, you have your product, and you know the performance that you can count on, depending on the cooling. And if you make an installation where you have some sort of obstruction, what will happen then? Is it okay? It's another example. And the last one, where you position the fan. I mean, it also matters really, really much. I mean, you can have the best heat sink, the finned heat sink, super optimized. But if you don't make the ducting and you place the fan in a bad way, I mean, and you lose all the good stuff that you have worked with and that the product manages. You can have perhaps a much lower performance. This is an example, just a picture of a design that we have worked with. It's a liquid cooled pin fin, and you see this colored striping. That's showing the way that it's a glycol water mix, how it enters, it goes up, and this is the area where we have the power conductors. And this is shown, so then you can see a lot of stuff. So let's see the next picture. I hope this is visible for you. This is really the same design. This with the pin fin heatsink. It's instead of fins, it has pins. So what you can see, what kind of information can you get from a simulation? I mean, it's really a lot. Actually, I think you can get more information from simulation than from a test, really, because you can measure almost whatever you want to measure. So in this example, I mean, you can measure how hot does it get where you have the components, what's the temperature rise of the liquid. You can measure also the delta pressure. The delta pressure, it tells you how much energy is needed to push your liquid through this heatsink, because that's a parameter. I mean, you have to pay with the size of the pump or the size of the fan, but you want to make that as small as possible and still be able to cool your components. Yes, so that's about it, I would say. Let's see.
So, yes, some conclusions then. Simulation is a must-have tool to drive development speed. Iterating the design frequently to maximize the use of simulations. Simulation adds value in the design process. Cost has been reduced significantly over the recent years, and start with small cases and grow the complexity as you upskill. Thank you.
Great.
That's it. Thanks.
Thank you, Staffan and Matthias, for a very engaging and technically insightful session. I mean, this clarity highlights how advanced thermal engineering is enabled for high performance, reliability, and compact system design in modern electrification. I'd like now to invite everyone in the audience to submit their questions using the Q&A tab to the right of your screen. All questions are sent privately, and I'll go through as many as possible during the time we have left here. So please go ahead and post your question now. And once again, thank you, Staffan and Matthias, for an excellent presentation. We have a few questions already in the chat, so let's start with the first one. Let me read here. Can you share an example where thermal simulation led to a clear cost or size optimization, such as reducing the heatsink size or using a lower cost fan or any other solution? What's your experience in this area?
I can take that. So without revealing too much, I can say that when we're working with our latest high voltage inverter design, we have made a heatsink that showed quite similar thermal behavior in real life as in the simulation. So in principle, we did the design right the first time.
Good.
And that's really not how it usually is. So it's quite saved a lot of time actually by using simulations and being able to getting the performance that we needed from start.
Thank you. We have a few questions here. So looking ahead, where do you see the biggest opportunity for further performance gains through thermal engineering? Is that like in materials, cooling concepts, or development of the simulation methods?
Should I take it?
Yeah, you can.
I think that I mean it's all over this, all areas really. It's materials. I mean they are getting better. I mean it's improving always. I mean it's the research and development. It's never ready. And also regarding cooling concepts, I mean things are improving. But you can also say in general it's physics in the background. So there are improvements and there are changes. But this is a really big revolutionary changes. They are not so common. And regarding simulation methods, they are improving really, really much. I mean, both from a user point of view, they are much easier to use. And also, second one, if you remember this with the small elements, that the computers and the simulation tools, they are getting so much quicker and so much better performance. So you're able to, you have to be less skilled to do this with how do you make this mesh. You get help from the system, it goes much faster. So it's really usability improving very much.
Good. Thank you. And if you mentioned that technology is improving, and not often that we get step changes in that, but we have a shift here from SiC to GaN semiconductors. How has your thermal design approaches changed compared to the previous generation of power electronics in the scope of cooling design and so on?
As I mentioned earlier, that SiC and GaN devices, maybe I didn't mention it, but it's first of all a bit more expensive compared to silicon, which means that the full utilization of the chip is a must to keep costs down. Second part is that both silicon carbide and gallium nitride chips are smaller in general than silicon devices, which means that the thorough analysis of the heat conduction is more critical, and their simulation is even more important than before, I would say.
So you need to have better control of your cooling system with these new technologies.
Yes.
Understand. Good. And the last question here. You highlighted earlier that early judgment of the cooling strategy is critical. But if you look at the most common mistakes you see when thermal consideration are addressed too late in the project, or tell us more about that part. So,
first of all, I mean, simulations, even though Staffan mentioned that the tools are getting better and better, it is still quite time consuming. So to have an idea of a reasonable heat sink, for instance, as a starting point of your design, or before you start your simulation, I would say, is important. Otherwise, you will probably fail somewhere, and you need to redo this and reiterate many times before you have the final goal.
Yeah, and don't start until you have what do you want to know?
Exactly.
What they're interested in, because that has happened. I mean, why are you making? Well, what's the question, really?
Yeah. So start with the question and start early and be curious about it. Maybe also experimenting with it so you have the knowledge and working with that.
Yes.
Great. Thank you so much. We don't have any more questions, but I would like to thank you sincerely for a good presentation and good discussions and answers here on the Q&A. So thank you.